Now let's perform type judgment on a more complex expression. The expression here is a recursive function which sums all of the numbers up to x, and here is a call to that function with 5 as the argument. Feel free to pause and read over the expression to convince yourself that it is the expression I describe. It uses letrec, booleans, numbers, and the equality operation, which is an exercise in the notes. We should expect the result of S5 to be of type nat, since this is a function that returns a natural number, but let's prove it. At the top here is the rule for letrec, and we'll put in other rules when we use them. This rule has 3 premises, but the first is just a definition of gamma prime in terms of gamma. To avoid rewriting gamma prime in full, I'll copy that definition here and then just use gamma prime wherever I need to. Gamma prime is a type environment with the type of S prepended to our original type environment. Our original type environment was empty, so gamma prime is simply a type environment with S defined as specified by the letrec. So S is defined as a nat arrow nat function. With that premise out of the way, we have 2 premises to actually prove. We must prove that the definition of S actually has the type that we specified with letrec. That's why the type is already given here. And we have to judge the type of S5. Now, even though we already know what type the function must have, it must be nat to nat, because we said so, we still have to prove it. This is an abstraction, so we use the rule for abstractions. The rule for abstractions says that an abstraction has type tau1 arrow tau2 if the declared argument type is tau1, and we can judge the body to have type tau2. In this case, we already know what both tau1 and tau2 are from context, because we know from context that this whole expression must have type nat arrow nat. The declared type of x is nat, so tau1 is nat, which is good, because it had to be nat. The declared type of the whole expression is nat arrow nat, so tau2 must also be nat. From this part of the rule, we should prepend the definition of x, the argument to our abstraction, to gamma prime. Again, to avoid rewriting, I'll just place the definition here and call it gamma prime prime. So, the premise is that the body has type nat in gamma prime prime. This expression is an if-then-else, so we'll use the rule for if-then-else. Again, we can already fill in tau, since the result type is already known, it's already been restricted. We need to verify that the condition is a Boolean, and that both branches are of the same type tau, which the context said must be nat. The rule for equality is an exercise in the notes, so I'll just leave it as a bit of a mystery here. Suffice it to say, the result of a comparison is a Boolean. Either they're equal or they're not, true or false. The fact that numbers are numbers is just an axiom. We can take that as rote. So that leaves us with this operation. This is a numeric operation, so we use that rule. The first premise, that our operation is a numeric operation, is obviously true, so we'll focus on the other 2, that each operand is a number. The left operand is x, so the variable rule matches. Looking up x in gamma prime prime, it is indeed nat, so this branch is done. The right operand is an application, so the application rule matches. For once, we actually need to determine a type instead of just verify it from context. Tau2 was constrained from outside this subexpression. Tau2 has to be nat, but tau1 we actually need to figure out. So, we have that S is of some unknown type arrow nat, and the rand is of that same unknown type. We start with the rator, which is the variable S. Looking up S in gamma prime prime, it's nat arrow nat, So we can fill in tau here, and the rest of tau here. If S had had some type that wasn't arrow nat, then this proof would have failed, and our program would not have type checked. Now onto the rand, which is a numeric operation again. Again, the first premise is uninteresting, and, as always, all numeric operations have a result type of nat, and demand that their operands are also of type nat. So once again, we're just verifying, not discovering. On the left is x, a variable, which is indeed of type nat in gamma prime prime. On the right is 1, and it's an axiom that numbers are numbers, so we're done with this branch as well. In fact, we're finally done with the whole recursive function, and barely even realized that it was recursive. We didn't really have to think about it being recursive. Here is where it recursed, and all we had to do was look up a variable. That's the magic of let rec. That's the magic of recursive definitions. If we can allow the variable to be defined within its own definition, then all we need to do is look it up. We're not quite done yet, though. To finish off, we still need to check the final expression here. This is an application, so we use the application rule. The rator has to be of some arrow type, and the rand has to be of the argument type to the rator. First, we'll check the rator, s. It's a variable, so we use the variable rule. Looking up s in gamma prime, not gamma prime prime. Gamma prime prime only existed within a sub-expression on the left. Looking up s in gamma prime, it's nat arrow nat, so we can fill that in here and here. Now we check the rand, and it's an axiom that numbers are numbers. Now we can return to the application here. Its type is the result of its rator, which is nat. And returning to the let rec rule, for the whole expression, its type is the type of the in expression, which was nat. This whole expression has type nat, but more importantly, the whole expression passes type judgment, including all sub-expressions, even our recursive call to s. So this is a well-typed program.